right, so in this video, we're going to talk a little bit about how when we have a differential equation like this, so second order, linear, homogeneous differential equation, and the coefficient functions here are real numbers, constants, and a is not 0, so we really have a second order differential equation. How we know some things already about how to solve those, but what I want to focus on in this video is what is really going on in the background with what happens when we get non-real R values. So when we're talking about the R values, what we're talking about is that you can write a characteristic polynomial for this differential equation. And so that would be AR squared plus BR plus C equals 0. And we started by showing that if y equals e to the rx is a solution to this differential equation, that happens if and only if this equation is true for whatever value of r we have here, where r is a constant. So we started by exploring what happens when you have a function like this, taking appropriate derivatives, substituting into the differential equation, and noticing that that's only going to make the differential equation true if this characteristic polynomial is equal to 0. And so when we have r values that are real numbers, if they're distinct real numbers, then we get y1 equals e to the r1x and y2 equals e to the r2x as two linearly independent solutions to this differential equation, provided the r1 and r2 are distinct. So we talked about, that's where we started, what happens when we have real numbers. We talked about also what happens when you have a repeated real number solution and how to handle that. And then what we sometimes skim over in class and in the textbook is what happens if the r values are non-real. So r1 and r2 are a plus or minus bi, where the lowercase a and lowercase b are not the same as the uppercase a and b here, but that this would be the non-real solutions for the characteristic polynomial. So how do we handle that and what happens here? All right, so I'm going to just start by taking r1 to be the a plus bi, and thinking about what happens if I put that into this form that we know how to use for real numbers. What happens if I instead substitute in non-real numbers here? So I'd have y1 is e to the a plus bi x. And so thinking about simplifying that. All right, so there's a little bit of algebra involved here. So I can distribute this x through so that I can rewrite that into e to the ax plus, I'm going to put the I in front so that it's in a sort of typical way that we might write a complex number. I'm going to use a property of exponents that we used at the beginning of the semester when we were solving some separable differential equations a lot, where we remember that if I have e to a sum of two things in the exponent, that we can sort of use one of those algebra properties that you learned in algebra sort of backwards and break that apart into e to this power times e to the second power. What's after the addition here? Usually you use that property this way, where you take two powers of the same base and combine, but we can break that apart. And then what we're going to use is actually the definition of what it means to raise e to an imaginary number. And so this is a definition of a complex exponential. You might have seen this in a pre-calculus class or a trigonometry class, or maybe calculus 2. Sometimes this comes up when you do series for exponential functions. So often the way you see it when it's written in a trig class or a pre-calculus class is with theta here. So e to the I theta is defined to be cosine theta plus I sine theta. All right. And so that's a definition. So there is some stuff, which is part of what's in Calculus 2, showing why that is a reasonable definition, way to define a complex exponential. But I'm going to use that to rewrite this e to the I times bx in terms of cosines and sines. All right, so e to the ax, and then here I'll have cosine. In this case, the theta would be the bx plus the I sine bx. And I'm going to go ahead and distribute through the e to the ax just to separate that into separate terms here. So I have e to the ax cosine bx. So I've got the real part plus, and then I times e to the ax sine bx. All right, and if we want to put parentheses around the bx here, we can, but you don't have to. Okay, so that is a solution. It's kind of a messy solution. It has an imaginary part with it, which we might not normally want when we're thinking about solving differential equations where we have real number inputs and real number outputs. But it is a solution to the differential equation. We started by examining what would happen, what our values would have to be in order for something like this to be a solution. So that's one of the R values. Our other R value was a minus bi. So I'm going to skip some of the algebra here and just to save some space to think about what would happen if I take R2 is a minus bi. Right, so I'll put in y2 is e to the a minus bi times x. And then essentially following through the same steps that are here, but I'm going to have a minus bx. So I will get here where I'll have e to the ax cosine of minus bx plus I times e to the ax sine of minus bx. Okay, then do a little creative use of some trig identities. Cosine is an even function. Cosine is an even function. So that's going back to some stuff from trig or pre-calculus, or thinking about what even functions are, maybe algebra, college algebra, or pre-calculus. Cosine is an even function, which means that cosine of negative bx is the same thing as cosine of bx. The cosine function in some sense can absorb the minus sign. It's not exactly what happens, but it's what an even function is. The sine function is an odd function, so that means that sine of negative bx is the same as negative sine of bx. So I'm going to put that negative all the way out front here. Minus I times e to the ax sine bx. Okay, so I have here two functions, y1 and y2, that are solutions to this differential equation. You can verify that. We started with that in class when we looked at what the R values would have to be in order to satisfy the differential equation. They are solutions to the differential equation. These two functions are linearly independent. You could show that by using the definition of linear independence, by using an Wronskian, or by just noticing that they are not scalar multiples of each other. So these two functions do form a basis for a solution space for this differential equation. However, they're kind of messy. Why are they messy? Because they have this imaginary term. And so remembering that a basis is not unique, that you could have more than one basis for a vector space, as long as you have the right number of objects that are linearly independent, they will still be a basis for that space. And so taking a sort of creative linear combination of these two functions will give another solution. So these are solutions, but they're not as nice as we would like them to be. So what I'm going to look for here is nicer basis for the solution space. All right, so if I take y1 and y2 and add them together, notice that the imaginary terms will drop out. The minus I e to the ax sine bx and the plus I e to the ax sine bx. And then I'll have 2 of this term. So maybe I don't want the 2 there. The 2 would be fine there, but I could let y3 be the sum of these two functions, and then I'm just going to multiply by 1/2 or divide by 2 if you prefer. So y1 plus y2. All right, so I'm going to add these two functions together because that'll make the I terms drop out. And then I would have 2 e to the ax cosine bx, but then multiplying by 1/2 will get rid of that 2. So I'll just end up with e to the ax cosine bx. All right, so when we went through problems in our notes, it indicates that this is a solution. It doesn't really indicate exactly where that comes from, which is what I'm trying to show you here. So similarly, I would like to do something that would maybe make the cosine terms drop out so that I end up with the sine terms here. Okay, so let's think about what we would want to do, how we would algebraically want to combine these two functions in a linear combination so that we get another function that's still in that set and that could be a nicer basis function for our solution space. All right, so I would like the cosine terms to drop out, so I would like one of these to be negative. So multiplying one or the other of them by -1. And really you could do that either way, but it might be nicer if I multiply the second one by -1, because then I'd have a plus here. So I'm going to do y1 minus y2. Okay, so if I take this function and subtract this function from it, the cosine terms will drop out. And then I would have I e to the ax sine bx plus, from the minus negative, I e to the ax sine bx. So that would be 2I times e to the ax sine bx. So in the same way that I multiplied by 1/2 to kind of clean up that coefficient in front of that one, I'm going to take y1 minus y2. When I do that, I would have a 2I coefficient out front. So similarly to how I got rid of the 2 by multiplying by 1/2, I'm going to get rid of that 2I by multiplying by this coefficient, 1/2I. And when I do that, I'll get e to the ax sine bx. All right, so these two functions that I have circled here are solutions to the differential equation, provided R1 and R2 equals a plus or minus bi are zeros of this characteristic polynomial. These are solutions. They are clearly linearly independent. They are not scalar multiples of each other. And so these form a basis for the solution space to this differential equation. Or we could say that these form a fundamental set of solutions to this differential equation. Or often the way we write that is that we would say that the general solution to the differential equation would be given by y equals c1 times one of these plus c2 times the other one. All right, so when you do problems like this in your homework, do not go through all of these steps. You can do it once or twice just for fun if you like, but on homework and on exams, when time maybe is a factor and you don't want to spend a bunch of extra time doing some fun but maybe unnecessary mathematics, recognize that when you get R1 and R2 being a plus or minus bi, non-real R values, that you can just go straight to this general solution or these two functions here for the fundamental set of solutions. So just go straight there. I just wanted to explain a little bit about what is really going on in the background, where those come from. So some stuff that maybe is a little back there in your memory, but just trying to explain why that happens the way it does.